Hello everyone, my name is Isaac Ngui. I am a senior computer science major at UW-Milwaukee, and I am here to talk to you about kinematic trajectory tracking control of omnidirectional mobile robot. So first off, a mobile robot is any robot with the ability to move from one point to another. So that could be something like a drone or a wheeled robot or a car, things like that. Recently they've increased in popularity due to their ease of mobility and high autonomy. Many tasks actually utilize those features very well, such as search and rescue missions, factory helping, and then planet exploration, and then coordination as well. And so in order for these robots to be able to do all those tasks, there's a lot of work that needs to go on in the background. And so what this work looks at is the act of trajectory tracking, which is ensuring that the robot stays on the path that it is designated to follow. And so the way we did this was that we derived a kinematic equation, which basically will tell us where the center of the robot will move when we move our wheels, or vice versa, where our wheels will move when we move the center of the robot. And so using those equations, we're able to actually tell our robot how far we want it to go and have it stay on a path. And so in order to do that, we generate the trajectory that we want the robot to follow. We split it into small segments with angles, and which can be seen in this middle section with the segment length and the direction angle. And basically that'll give us a constant distance that our robot needs to travel, and then the angle will be changing depending on the curvature of the trajectory. So using these pairs, we can actually feed that into our kinematic equations, and that'll tell us the velocities of each wheel as well as the motor encoder counts that these wheels should reach before stopping. So the wheels that we have on these robots are capable of counting how many times they have moved in one revolution. And so there's we know the amount of ticks that'll go off in one revolution, and so using that knowledge, we're able to calculate the velocity of our wheels by doing some basic math using those tick counts. So we take these velocities and encoder counts and we send them to the robot from MATLAB using Wi-Fi compatible microcontrollers. They're called ESP8266. They're very, very cheap microcontrollers that really are very useful for a lot of applications involving Wi-Fi. And one of the reasons we chose those chips was because if we ever wanted to scale this up to use more robots, Wi-Fi is very nice at allowing very fast transfer speeds of data, as well as being very you're able to use a lot of different devices on a network. We were originally looking at Bluetooth, but we decided that Wi-Fi would be better. So once the robot gets those values, we pass them into what's called a proportional integral derivative controller, which basically we give it a set value that we want it to. So we tell our motors we want them to move at a certain RPM, rotation per minute, and then what the PID controller does is it takes it looks at the air and the current speed of the motor, and it'll try and bump it up until it and force it to maintain the specific velocity we want. So we basically tell each wheel we want it to go to that velocity and maintain it, and then while it's actually moving at that velocity, we will be counting all of the counts until we reach a certain desired count, and that count is basically from the kinematics we're able to calculate the exact position that our motors should be in where the wheels should be. And so using that calculation, we're actually able to find the exact number of encoder counts that should have passed by when we get to that point. And so we stop our motors when we get to those points. So in our methodology section, we have the kinematic equations. So they're kind of long, weird equations, but basically the phi dots are the angular velocities. So if you were to spin a wheel, that'd be the velocity of that wheel, the angular velocity, sorry. Alpha is the offset of each wheel from the origin. So our wheels are set 120 degrees apart. So alpha of the first wheel would be 0 because it would be on the baseline point. Alpha of the second line, or the second wheel, would be 120, and then alpha of the third wheel would be 240. So theta and theta dot are the orientation and the rotational velocity of our robot. So that's going to be, we designate the wheel that's on the baseline to be the front of the robot. And so basically any rotation, so wherever that front wheel is in comparison to the baseline global x-axis, will be an orientation change. And then if we have like a constant orientation change, we'll have a rotational velocity. And so one of the cool things about these robots is that due to their the type of wheel, they have omnidirectional wheels, hence the name. They're allowed to move in both translation, so left, right, up, down, as well as rotation simultaneously. So we can actually tell it to change the direction the robot's facing while moving in a different direction, which is really nice and very cool. It has a lot of applications. Our big R and little r are the radius from the center of the robot to the wheel, and the radius of the wheel. And then x dot sub L and y dot sub L are the local x and y directions. So using all of those, we're able to calculate the angular velocities for each wheel, which we then can find out the exact number of encoder counts that we need to reach in order to stop our wheels from moving. So we have to break down our trajectories into little segments, and so it's basically we have the direction that we want our wheel to move at, and there's always a constant length because we break our segment or our trajectories down into specific size segments, and then there's a angle from the global x-axis, which we call the baseline, and that tells us the exact direction that we're going to be traveling in, and the speed is always constant, and using that we're able to determine how fast our motors need to be moving. And then in the bottom we have the PID controller, and that uses the past and present error to maintain a set value. And again, our motors have encoders which count the ticks, and in the bottom we show a picture of what that actually looks like. So there's an input and then there's a feedback. So the feedback is going to be the value that our system is outputting back. So if we wanted to have a motor maintain a certain speed, let's say 60 miles per hour, a good analogy for a PID controller is like cruise control on your car. So let's say you want your car to go 60 miles per hour and it's only going at 55. What will happen is there will be error that gets passed in. So it's what you're currently moving at versus what you're desiring to be looking at. So let's say our car was only moving 55, we wanted it to be 60, our error would be -5. So using those, the first term on the top is Kp, which is proportional. The middle term is going to be our integral, and the last term is going to be derivative. And using a combination of those three and summing them up, we'll be able to push our set velocity that we want to move at, so 60, and we'll push our whatever we're outputting up until it meets that 60 and stays there. So it won't go higher and it won't go lower than that value. So we perform simulations using the kinematics and the PID controller. So the first simulation we ran was on a sine wave controller trajectory. And so this video right here is showing the sine wave controller, and as you can see, it shows that our robot stayed on the trajectory very well, and it always kept one wheel on the path that we were trying to follow, which is exactly what we were looking for, and it worked out exactly how we wanted it to be. And the second simulation we ran was on a circle, and so as you can see, the same thing happened. We were following this curved trajectory, and the robot started at the center and went all the way around until it reached the exact end point, and the center of the robot always stayed on the trajectory. So this is helpful for us because it shows us that we'll be able to move around corners without problems, as well as if we ever wanted to move in very highly constrained areas where there's not a lot of movement, our robots will be very good at moving in those locations. So this research basically shows that our kinematics are working properly, and the simulations have a good showing that our experimental results will turn out just as well. It also shows that our methods for breaking down the trajectory works, although there are some downfalls of that method, specifically for very, very sharp turns. But most of the time, robots won't be making those sharp turns. But if that ever comes up, it will be something we'll look at. And then in future research, we plan to perform the physical tests. Unfortunately, we didn't have much time due to the whole outbreak, but as soon as we get back, we're going to definitely test that on the physical robots. And then, but we have tested our PID controller, and we have that working very, very well. And it runs really, really quickly, which means that we'll be able to get a high precision of accuracy on the set point that we want to maintain. And then eventually we plan to add a robotic arm on the top of the platforms and use these robots for coordination of those robots. Thank you.